Okay, so we have this problem. We want to determine the moment of inertia of the shaded area about the x-axis. So how do we get the moment of inertia? So if we're getting the moment of inertia about an axis, let's say the x-axis in this case, we need to get the integral. This is over that area we're supposed to rotate. And then I like looking at it as the radius squared and then dA. The only thing is that the radius, if you're getting the moment of inertia about the x-axis, the radius will mostly turn out to be an expression or a value of y, an expression for y or a value of y. So mostly that is what you expect. That is why mostly you have a formula where you have y squared if you're getting the moment of inertia about the y-axis, about the x-axis, I mean, and you have x squared if you're getting the moment of inertia about the x-axis, about the y. Sorry, I'm swapping them there. If you're getting the moment of inertia about the x-axis, you have the radius as y squared. Yeah, I'm saying radius. You have the radius as y, so the radius squared will be y squared. But if you're getting the moment of inertia about the y-axis, the radius in this case will most likely be an x. So you have the radius squared, which will be x squared dA. But why is it actually a y? So let me start with it still being r squared. So when we are choosing our radius, it depends on the section we are going to be working with. So since we want to rotate about the x-axis, so this is about the x-axis, the best choice is to work with the horizontal section. So a horizontal section here, observe that if you picked a point right along the curve there, and say this point will have coordinates x, y, observe that for that point, there will all be an equal distance from the x-axis. So the distance from the x-axis to all points along that road or along that section, assuming it is a very thin section, all points there will lie the same distance from the x-axis. So because of that here, the radius is going to be y, because again, observe that that same distance from the x-axis to where those points are corresponds to a y value. So this is why here the radius is a y. If you had gone with a vertical section when getting moment of inertia about the x-axis, here you'd be forced to use the parallel axis theorem. Why? Because if you picked a vertical section, now observe that the points, even if you were to say you pick a point here, the x, y, notice that the points, even if you say this is a thin section, the points, some points will be further away from the x-axis, some will be nearer to the x-axis. So points are not at the same distance from the x-axis. So to do that, you'd have to use the parallel axis theorem to get the moment of inertia about the x-axis if you're using a vertical section. So for our discussion, for simplicity, we will evaluate this using a horizontal section. For practice and more understanding, I'd advise that you also try to evaluate this using the parallel axis theorem to see if you can obtain the same solution. Should anyone insist in the class, we can still do it together so that you see how it would turn out. But let's start with using a horizontal section where here the value of y here will correspond with our r. So r here is equals to just y. So what else is obvious? We know to say here you have an x coordinate there. So for the horizontal section, its length, since it's from 0 to x, its length is x. Its thickness is in the vertical axis, so it is a dy. So when you get dA here, it will be the length multiplying a dy there. So that will be the expression for dA. The radius, however, as we saw, is just a y. So the radius squared will be y squared, but dA comes with x dy. Since we have to integrate with respect to y, we don't want to have the other variable in play. So we want to rewrite x in terms of y. The best thing is we did select our x to lie along the curve, this curve, and we do have the relationship between y values and x values for this curve. So that is the relationship. So from this relationship, we can easily make x subject by square rooting both sides. So we have the root of y to the power 3, or we can view this as y to the power 3 over 2. So in place of x, we can now put y to the power 3 over 2. So this x here has now been written in terms of y, and it came out as that. Any questions up to there? Okay. So if we followed up to here, we can combine these two. Since we are multiplying y squared and y to the power 3 over 2, same base, we can just add the powers. So we're basically going to have 2 plus 3 over 2. Denominator is 2 there. And then we're going to have 4 plus 3. This looks like a 7 over 2. So please verify that. So once we have simplified the expression, we are integrating from what to what. Since this is a dy, the limits of integration is the smallest value of y to the largest value of y. So in this case, the smallest value of y, when we check here, the smallest value of y is from the bottom, which is a 0. And the biggest value of y is a 1, and that's a 1 meter. So we're integrating from 0 to 1 meter. So when we integrate, we know to the power, we have to add 1. And then we'll divide that new power down as well. And then this is from 0 to 1. Even if we don't simplify that power, when we substitute 1, this is going to be 1 to the power 7 or 2 plus 1 over. In the denominator, would have to simplify that. So that's going to be 9 over 2. So here, 1 to the power, that will still be 1. So this will be equals to 2 over 9. And the units, remember moment of inertia, we will have, since it is r squared dA, basically it's the unit for length squared and the unit for area multiplying. So it will be a power 4. Since the upper limit came with a meter, we expect this will have a meter to the power 4. So this is how we would obtain it. Any questions on that one? Would you want to see it using the parallel axis theorem? Or you would try it as you practice? I didn't get that. We can do it in parallel. We do it together? Okay. So if we're going to use the parallel axis theorem, how is it going to work? So now we will use a vertical section. So if you had selected a vertical section, what would have been the case here? So, well, it becomes a little bit complicated actually, or not complicated, a little bit tricky. Unlike the one we're just from looking at, which was easy. So how is it going to go? Firstly, once our section has been selected, we'll pick a point right there. This point will be our x, y. The point is selected strategically so that it is on the curve, so that we'll be able to use that expression. Next up, the section we have picked has its own centroid, has its own center. So this is going to be the centroidal axis for that particular section we have selected. So for the section we have selected, we are going to use the parallel axis theorem. So for the small section we have selected. So remember the parallel axis theorem says the moment of inertia of an object about any axis can be obtained if we know the moment of inertia about its centroidal axis. So we're taking this to be the centroidal axis for that particular object. The only condition is that the centroidal axis has to be parallel to the axis we are targeting. If we can do that, then we can only add, or we only have to add the product of the area of the section with the distance between the two axes squared. If the two axes which are parallel are like this, then the distance between them will be a distance in terms of y. There's why sometimes if it's the x and so on, you see you have a subscript of a y there. So this is, in general, what the parallel axis theorem points out. But observe that the way we're going to deploy the parallel axis theorem, we're not going to deal with the overall structure. Because let me give you an example. If you had, let's say, a shape like this one, you want to get its moment of inertia about an x-axis that is way at the bottom here. Way at the bottom here. Using the parallel axis theorem, if this is the original x-axis, you first need to get the moment of inertia about its centroidal axis. The centroidal axis has to be parallel to the axis we are targeting. So this is the centroidal axis. So first you get the moment of inertia about the centroidal axis. Once you get the moment of inertia about the centroidal axis, now we can say the moment of inertia we want, which is about the bottom axis there, will be equal to the sum of the centroidal axis, or the moment of inertia about the centroidal axis, plus the area of the structure, which is a whole structure here, multiplying the distance between the two axes, the distance between the blue axis and the white axis there. So this will be the distance t. Now, this is the theorem itself, but we are deploying it not for the whole structure. To use it here, we are defining a different shape, a rectangle there. So we're saying the rectangle we are getting the moment of inertia for, it's actually a differential area. So we're using the parallel axis theorem on a differential area. So meaning we'll get the moment of inertia for the differential area using the parallel axis theorem. So it will be x is equal to the differential moment of inertia, or let me say the moment of inertia about the centroidal axis for that selected section, plus the area of the differential area. So this is its area there, multiplying the distance between this and this for the differential area. So this is going to multiply the distance between them squared. So basically this is going to be, I can keep it d for now. We'll find what it is later on. So let's keep it as d squared. So this is the concept we have to use. Any questions on that? the distance d here is the distance from the axis we're evaluating about, and here the axis is the x-axis, not the base of the section we have selected. So it's from the x-axis to the centroidal axis. So if the section we pick is this section here, or this small one there, then the distance will have to be from here up to its centroid there, not this one here. But if the section we have selected is this small section, then the distance will have to be from the x-axis up to where it is there. Yeah, you did have a point there. Okay, so once we are certain on the expression we're using and what each character represents, then we can move on to try to find the different parts for this. I think I wanted to explain that in details, especially because changing it from the original, from this version to the one that has differentials, I think it's the one thing that I think, for me, I think I struggled a bit to follow. But once I saw it, it was so obvious what was happening. Okay. So do we have any other questions before we proceed? Okay. So if there are no questions, then let's proceed to see how we would deploy it. We've already seen the expression we're going to use. The only thing that we need to find now are the different parts for that expression. So let's bring back our diagram and just clean it up a little bit. We did define our section to be a vertical section in this case. And we said we pick a point somewhere there, x comma y. The centroidal axis for the differential section will be here. This is where our y tilde is. So remember our expression, we're going for the moment of inertia for the differential section about the x-axis will be equal to its moment of inertia about a centroidal axis plus the area of the differential section multiplying the distance between the x-axis and the centroidal axis. Now observe that in this case, the distance from the x-axis to the centroidal axis will actually correspond to y tilde. That would be what the distance is. Even if our section was to be somewhere here, y tilde will be the centroidal or the y coordinate of the centroid for that section. So in each case, the distance will keep on being y tilde in this for this case. So remember, it's the distance being squared there. With that done, what is dA? So when you look at our vertical section like this, its thickness is in terms of the x-axis, so we'll get a dx. It's changed, right? Its thickness is in terms of the x-axis. Then, how about its height? Notice that its height first is in terms of y, so it's like from y1 to y2. But these values of y cannot be expressed in terms of x. Above all, we're going to have a dx there, y1 to y2. So what is y2? Notice that y2 is constant, or y at the top there is constant. It's always 1. So y2 is a constant 1. But y1 depends on the function, on the curve. And the curve is y to the power 3 is equals to x squared. So you make y subject here by raising everything to the cubic root. In other words, this would be the same as x to the power 2 multiplying 1 to the power 1 over 3. And this will basically be x to the power 2 over 3. So that is what y will be equal to. So this y1 will be the same as x to the power 2 over 3. So the length or the height of this section will be the top, which is 1, minus the bottom, which is x to the power 2 over 3. With this done, we can get dA. dA will now be equal to the length, which is 1 minus x to the power 2 over 3, multiplying the thickness, which is dx. So we now have dA. Next, what is going to be our y tilde? So we now want to find what our y tilde is going to be. So observe that y tilde is not fixed. Y tilde will depend on which section we are currently at. So we need to find the expression for y tilde. So how do we get y tilde? So it's the same expression, the same rectangle. But this time around, we will not get the difference to get the height. We're looking for the midpoint of that rectangle. To get the midpoint of the rectangle, since that is where y tilde is, to get the midpoint, we know the coordinate of the top is given by y2 is equals to 1. The bottom will always be given by y is equals to x to the power 2 over 3. So its midpoint, remember how you get midpoint between two values? You add them, then half them. So we'll have to get 1 plus x to the power 2 over 3. We've added them, then divide them by 2. This will tell us exactly where the middle is. So this is how we'll get that midpoint. So we have obtained what y tilde is. With that done, the only other thing left is this part. The moment of inertia about the centroidal axis. So we know to say the moment of inertia of a rectangle about its centroid will be given by 1 over 12 BH. So this is the moment of inertia to the power 3, of course. Moment of inertia of a rectangle about its centroid. So this will be for our shape like this. So moment of inertia about the x-axis. So it will be given by that. So when we change this, the base here is basically going to be the thickness, which is going to be our dx. And then when it comes to the height of the shape, we've seen the expression that will give us the height there. So the height for the rectangle will basically be given by the difference between the top and the bottom, given by that. So we see that in this case, for the moment of inertia about the x for that part, the centroidal x, will be equal to 1 over 12 multiplying the thickness is the dx, but the height will be given by 1 minus x to the power 2 over 3, but the height has to be raised to the power 3. So this has to be to the power 3. We can keep it like this and substitute. We now have our di is equal to, where we have this centroidal moment of inertia, we'll take the dx to the far end, 1 over 12, and then this will be 1 minus x 2 over 3 to the power 3 dx, then plus what follows is dA, the differential area. Did we get it? Yes, we did. So that is 1 minus x to the power 2 over 3. There's no power there, dx. And then finally, the distance between them squared. The distance between them, we did get that distance. Did we highlight it? The distance between the axes, yes, we did that. We said it's half of the sum there. So that is going to be 1 plus x to the power 2 over 3 over 2. But remember, this distance has to be squared. So this is what we end up having. di is equal to 1 over 12, 1 minus x, 2 over 3, the power 3 dx. Then this part, you can square the dx goes to the far end. Here, when you square, you're going to end up with 4 over 3. You can leave it like this anyway for now. So I have plus 1 minus x, 2 over 3, multiplying. Now, actually, we can combine these. This is minus, that one is plus. That's okay. 1 plus x to the power 2 over 3, but this has to the power 2. The 2 in the denominator, I can square it in advance. That's going to be a 4 dx. So this is where we are. At this stage, you just have to be very careful in terms of how you simplify this, because if you make a mistake, then you're gone. So the one that you're looking for, which is I, will be obtained by performing an integration here. Ix, when you integrate everywhere, this will be 1 over 12, the integral of 1 minus x 2 over 3 to the power 3 dx plus 1 over 4 here, the integral of 1 minus x to the power 2 over 3, and then 1 plus x to the power 2 over 3 squared dx. In terms of limits of integration, we're integrating with respect to x, so it becomes the smallest value of x, which is 0, to the largest value of x, which is 1. So this is going to be from 0 to 1, from 0 to 1. Now you end up with this situation or this expression. If you are stressing on how you're going to integrate this, it is actually very straightforward once you see what you have to do. If you cannot have a straightaway method of integrating, the highest power for the first part, for example, is a 3. So this is the power 3. Expand it. So expand it so that you can integrate term by term. In the same way, here, if you cannot find a suitable way of integrating it, expand, then simplify so that you distribute the integral. This is raised to the power 2. You can easily expand it. In the same way, then expand by multiplying it with that so that you integrate term by term. That becomes very easy. So try to see if you can evaluate the integration here by expanding first and then working it out. Is it something you can do, or you still want us to do it? I think the deployment of the parallel access theorem we have done. Now here it's a matter of, are you able to integrate? So if you're going to expand, how would it turn out? This is from 0 to 1. Let's expand. So expand the first one first. The method you can use to expand, completely up to you. I'll go with the binomial. I have 1, 2, 1, 1. So I'll just use these coefficients since I see that's a power 3. So I'll have 1. And then this is going to be 1 will multiply 1 to the power 3. And then I'll have plus. Next I'll have 3. And then this will be 1 to the power 3 multiplying minus x to the power 2 over 3. This now, instead of power 0, now it have power 1. Then plus 3 again, 1 to the power 2. So I think you can keep it 1 to the power 2. So 1 had power 3, now it had power 2, now it should have power 1, and then the minus x to the power 2 over 3, now the 1 with power 2. And then finally, coefficient will now be 1. 1 will now have power 0, and then the minus x to the power 2 over 3 will now have power 3. This is all just for the first part. I haven't touched the second part. So what do I have here? In the first part, 1 over 12, 0 to 1. This is 1. This becomes minus 3, x over 3. Then this becomes plus 3x. This becomes 4 over 3. So just check through how I'm distributing and simplifying. 3 will negative will become positive when you square it. And then so the coefficient will be 3. 2 becomes 4 when you square that. This becomes minus when you raise to the power 3. And then this will be x to the power 3, and 3 there will cancel, leaving it to the power 2 dx. We can simplify this, and actually we can integrate this first part. So this is now 1 over 12. When we integrate, this is 1 minus 3x to the power 2 over 3 plus 1 over 2 over 3 plus 1 plus 3x to the power 4 over 3 plus 1 over 4 over 3 plus 1, and then minus x to the power 2 plus 1, which is 3 over 3, from 0 to 1. This is just the first part. Don't forget the rest of it. So this is now 1 over 12. The top part will be 1 when I put 1 there. So all I'm worried about is what comes from here. This will be 3 there. So 5 over 3. So 5 over 3. 5 over 3 becomes 3 over 5. Plus, here, this will also be 1. So from the denominator, I will have 3 will multiply 1. So I have 7 over 3. 7 over 3 becomes 3 over 7. Then minus, this will remain 1 over 3. So 1 over 12. So this is now 1 minus 9 over 5 plus 9 over 7 minus 1 over 3. So we can simplify this to see what we're going to get there. Can you guys simplify? What are we going to get here? So the first part has reduced to 4 over 315. So of course, the same unit, so take this as a millimeter to the power, not a millimeter, this is a meter. So this will be a meter to the power 4. We now want to do the same thing for the second part here. What are we going to get? So these, remember, are going to add up, so we're going to add them up after we are done. So just focus on the second part, then we'll add up afterward. Expanding this, we'll start by expanding the second part there, that is quadratic. So keep this the way it is. This becomes 1 squared, which is still 1, multiply them, then double them, so it will be 2x to the power 4 over 3, and then square that last part. So you square that last part, it becomes x to the power 4 over 3. This was fast to expand, so now we'll just distribute, or expand it here one more time. So this will be 1 over 4 from 0 to 1. 1 multiplies everything, that's 1. 2x to the power 2 over 3, and then x to the power 4 over 3. Now, negative x has to multiply everything, so it would be minus x to the power 2 over 3. When you multiply the second part, note that it's x over 3, x over 3, even x over the 2 shows up, but now it will be x to the power 2 over 3 squared, which is just going to be 4 over 3. And then now minus multiplies there again, minus again. So now it's x multiplying x to the power 2 over 3, multiplying x to the power 4 over 3. Same this, so we'll just add the numerator, so it will be 6 over 3. 6 over 3 is just 2. Did you see that? Any questions there? The ones which are similar can simplify. So that now we have 1 over 4, 0 to 1, 1, 2 over 3, or 2x, 2 over 3 in this will simplify. And then x 4 over 3, and the other one will simplify as well. And then we'll have this one here. So please keep on checking what I'm doing to make sure that I'm doing the right thing. So at this point, we can now integrate. Any questions up to here? Have you observed anything fishy? Are we good up to this point? Okay, looks like we're okay. So now it's just integrating. This will be x. This becomes x to the power 2 over 3 plus 1 over 2 over 3 plus 1. This becomes x to the power 4 over 3 plus 1 over 4 over 3 plus 1. Then this becomes x to the power 3 over 3 from 0 to 1. In the same way, plug in 1. This will be 1 here. And then this will be 1 in the numerator over, this will be 3 there, 5 over 3. This is plus. Please be able to catch those. I ended up putting a minus there. So this one now, I hope I didn't do anything. So negative, 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 negative. Okay, that's okay. So this one will now be 1 here as well. In the numerator, in the denominator, 3 there, 7, so 7 over 3. And then the last one there will be minus 1 over 3. Okay. So now it's just simplification. 1 plus 3 over 5 minus 3 over 7 minus 1 over 3. Oh wait, why do I still have these limits? No need for them. We've substituted. So what are we getting when we evaluate this? So 22 over 105. Okay, so once we have the two expressions, so here we'll have plus 22 over 105. So what are you getting when you add the two expressions?
Two over 9.
2 over 9. I had very little hope. Actually, it's 2 over 9. Yeah, sure. had very little hope that this was going to reduce to 2/9. Have you guys verified?
I've done it for the second time. It's due to overnight.
Great. You see, I knew this is supposed to give us the same answer, but so many numbers, I was almost certain that would have made a mistake somewhere. So I was expecting that maybe it was going to throw us off somehow. But as you have seen, both methods, the parallel axis theorem and the straightaway method, still reduce to the same answer. The only difference is that clearly one of them was faster than the other. I hope you were able to see which one was faster than the other. But in deploying them side by side, I hope you also saw the right way of deploying the parallel axis theorem. This way of deploying it with the differentials in place, it only applies when you are using sections to deploy the parallel axis theorem over an entire area. But if you're going to use the whole area, like I keep going back to a rectangle itself, if you get to using the parallel axis theorem for a rectangle itself, there is no need for you to use the differentials, because basically you will just relate the moment of inertia about the x-axis to the moment of inertia about its centroidal axis. Another example where I would say you go about it without deploying the differentials is think about a shape whose moment of inertia about the x-axis is already known. Then in that case, you can say that, okay, since I know to say for this structure, the moment of inertia about the centroidal axis takes this form, then about another axis somewhere else, it would be obtained using the parallel axis theorem this way, as long as these two axes are parallel and I know the distance between them. But if you don't know the equation in advance, then you would have to deploy the differential version of it to get the answer. Okay, any questions?